But this begs the question, since this is completely phenotypically based, are the genetics of this adaptation shift? Okay? And so here are two cartoon examples of how they could or could not have high parallel genetic evolution. So on this side, I illustrate low parallel genetic evolution. So these two descendant populations are adapting with 4 loci. And in this population, you only had a genetic change at the first and second locus, whereas in this population you had it at the third and fourth locus. And then in contrast over here, you have it at the first and second locus in both populations. Okay? But how common is parallel genetic evolution in natural systems? So very familiar to us is parallel evolution in human skin color. So you have a change to a lighter skin color from dark African skin color in Northern European populations, and again in East Asian populations. And of the 2 loci that are known to cause this change, they are different in the 2 populations. And similarly, you have a phenotypic change in deer mice to whiter colored sand on the beaches, and you have, depending on which populations you look at, you either have 0 loci share or 1 locus share. And you can continue this story with Mexican cavefish, white-sands lizards, and perhaps the example that best epitomizes what the models that I'll illustrate to you today is the 3-spined stickleback. So 3-spined stickleback have a population in the ocean, the saltwater ocean, and they have repeatedly colonized freshwater lakes. And of the 4 loci that are known to cause reduced skeletal morphology, I think there's lots of different changes that have occurred, but I think this is for the body armor. Of the 4 known loci that cause this, depending on which populations you look at, they either only share parallel genetic evolution at 1 locus or 2 loci. So if you look across the examples, about half the loci are shared. Okay, so should we be surprised by this non-parallel genetic evolution? So I'm going to begin answering this question by building a very simple model where I start with an ancestral population that has a single locus that's dominated by the little a allele, but it might have a low standing genetic variation with the big A allele, and in the descendant populations, the big A allele has fixed in both of them. And then there is linear selection in these descendant populations, and then with the Wright-Fisher model, I can write down what the probability of fixation of this big A allele is in the descendant populations. And since parallel genetic evolution is simply a repeated fixation event, I can just simply write down the probability of parallel evolution by raising the probability of fixation to some power. Okay? But that's kind of a complicated equation, so let me break it down so we can understand what it means biologically. So I've separated out 3 terms here that I find that are important. The first term is this red term, which is n, which is the population size, and it times beta over alpha, which is the selection gradient. So together, this describes the stochasticity of the system. But I want you to close your eyes and just pretend this is selection, okay? So if you have really random evolution or low selection, which is over here, then you have very low parallel evolution. And then if you have high selection, which corresponds to deterministic evolution, you tend to get high parallel genetic evolution. The middle plot here describes the allele effect of allelic effect size. And so if you have a minor allele, you tend to get lower parallel genetic evolution. And the larger the effect of the allele, the higher the probability of parallel evolution. Okay? And then the last parameter that's important is the initial allele frequency. So remember I said that I was allowing for standing genetic variation in that big A allele in the ancestral population? Well, the higher that allele frequency is, the higher the probability of parallel evolution. And that generally makes sense. So do these this is all based off of that single locus model, so do these same trends hold true for a multi-locus model? And I'm not going to illustrate to you what that multi-locus model is exactly, but they do, okay? And this leads to some really, really cool dynamics. So if you look at these 2 plots and say, hey, Ailene, you screwed up. Those are exactly the same plot. That's not a mistake. They are exactly the same, but I informed them using different parameters. So on the left-hand side, I have weak selection, and then simply by changing those other parameters, I got these plots to look exactly the same, okay? And so that is kind of unfortunate in some respects, because we can't say, oh, you get lots of parallel evolution, therefore you have strong selection. that is not an equal sign, okay? And so what do? Well, so from here, I started developing a Bayesian method that allows me to take some evolutionary parameters and some data and let you determine how strong selection is driving parallel evolution, okay? So to get my data, I take my ancestral populations and my descendant populations, and then by looking at which loci have fixed in my descendant populations, I wrote down a 1 if you got the rare allele to fix, so the big A allele to fix, and a 0 if the ancestral allele is present. And that was my data. And then I used my model that I gave you earlier to write down a likelihood surface. And then I combined that with the prior distribution for the strength of natural selection, the eta term. And this gives me a Bayesian estimator for that eta. Okay? So a Bayesian estimator is great, but it's only great if it actually predicts what you want. So I had to test to make sure that it actually gave me accurate estimates. So I did this for data where I only had data for 2 loci, 4 loci, and 8 loci. And in general, it works pretty good. The more loci you have, the better it works. The blue line here is just the standard regression line, and the red line is what a perfect prediction would be, which is just eta, your estimate exactly equal to the true value. And so, as you can see, as you get more and more loci, it looks better. But this Bayesian estimator is completely based off of my model. So what happens if I violate some of the assumptions of my model? And so I did that in a bunch of different ways, and it turns out it's pretty dang robust, which is awesome. Okay? So in conclusion then, parallel evolution depends on 3 basic parameters. It depends on the strength of selection, it depends on the allelic effect sizes, and it depends on the initial allele frequency, the amount of standard genetic variation. And then these same trends hold true both in single loci cases and multiple locus cases. And then using this, we can develop a Bayesian estimator that allows you to take parallel genetic evolution and translate that into the strength of selection. So with that, oops, wrong direction. I would like to thank the members of my master's committee, and thank you very much.